Hello everyone, let's try another review problem. Here I'm giving you the function f of x is equal to the cubed root of x squared on a closed interval from 8 to 27. Explain how and show how f of x satisfies the hypotheses of the mean value theorem. And then find each value of c in the interval, the open interval from 8 to 27, that satisfies the conclusion of the mean value theorem. So go ahead and pause the video and work on this problem. All right, if you need more time, pause the video again. If you're good, let's take a look at this. So we're given a closed interval and f is continuous on the closed interval. On the closed interval from 8 to 27. Then off to the side, let's just go ahead and state what f prime of x is. So we could think of this as x to the 2/3. So then we'll get 2/3 x. 2/3 minus 3/3 will give us a negative 1/3. Or this becomes 2 over 3 times the cubed root of x. And we're good because as long as x isn't 0 and we're in between 8 and 27, so we're good. So we could say and f of x is differentiable on the open interval from 8 to 27. All right, so actually it was a good thing that we found f prime of x. So now we could say that, again, we want to know where the slope of the tangent line is equal to the slope of the secant line, or f prime of c is equal to f of b minus f of a, all over b minus a. So we have f prime of c, since we found f prime of x, that's just going to equal 2 over 3 times the cubed root of x. And then the slope of our secant line is f of 27 minus f of 8 over 27 minus 8. So again, f of x is equal to x to the 2/3. So f of 27 becomes a cube root of 27, which is 3. 3 squared will give us 9. Cubed root of 8 is 2. 2 squared is 4. And then 27 minus 8 will give us 19. So we get 5/19. So we're going to go ahead and set, I still wrote an x over here, that should be a c. So we're going to set those two equal to each other. So now 2 over 3 times the cube root of c is going to equal 5/19. We could cross multiply here for a second. So we're going to get 38. 2 times 19 is going to equal 15 times the cube root of c. And then we'll divide by 15. So we'll just flip it around this way. Cube root of c is going to equal 38/15. We simply cube both sides. So c is going to equal, and we'll just leave it like this, 38/15 cubed. So there's our value of c. All right, let's take a look at the AP problem I assigned yesterday. Here f of x is equal to tangent of 2x. We want to find f prime of pi over 6. So f prime of x is going to equal secant square of 2x and then times 2. So this is 2 times secant square of 2x. And then f prime of pi over 6 becomes 2 times, and we can write this as secant of 2 times pi over 6, this whole quantity squared to make it a little bit easier. So this becomes 2 times secant of pi over 3 squared. And then we could turn this into, let's work with cosine. So we know secant of pi over 3 is the same as 1 over cosine of pi over 3. So cosine of pi over 3, that's just cosine of 60 degrees, should be 1/2. So then this becomes 1 over 1/2, or it's just 2. So then this becomes 2 times 2 squared, which is 2 cubed, or 8. Giving us E. All right, so hopefully you had time to look at my solutions with work to 43. And yesterday I signed number 44. So here are the answers. Part of today's assignment is to go back over and check your answers, correct it if necessary. So please let me know as you're correcting this if you have any questions. All right, so we're going to move on to section 4.3 today. Yesterday I gave you guys the quick review at the beginning of this, so you could check those answers. I will have posted later today or tomorrow, so you guys can definitely check over the weekend, the quick review solutions with work. But if you have any immediate questions, please email me. I also had you read pages 194 and 195, so I want to talk about this theorem, the first derivative test for local extrema, what we've been looking at. At a critical point C, if f prime, if our derivative, first derivative, changes sign from positive to negative, then f has a local max value at C. Or we could phrase this as f is changing from increasing to decreasing. But notice the wording here. F prime, our derivative, our first derivative, changes from positive to negative. Or we could say as f changes, not f prime, but f changes from increasing to decreasing. Both of these are acceptable, especially as explanations on the AP exam. They like to see either or. The very first way that this is worded, though, really shows that you understand what's taking place with the derivative and how that affects or relates to our function. Likewise, for 2, if our first derivative changes sign from negative to positive at C, then f has a local minimum value at C, or our function f changes from decreasing to increasing. But again, pay attention to the wording. And again, it's at C, therefore we have a local min at C. Item 3 just says if our first derivative does not change sign, then we have no extreme value at C. So it can change if it's still increasing, increasing, or decreasing, decreasing. Notice what's happening here, though. We still have a derivative defined. We're just going from concave down to concave up, and we're going to talk about concavity today. Here, there's, again, where f prime is undefined, but we're still decreasing and decreasing. Now, we can have endpoints here that can change things a little bit. So what this is saying, at a left endpoint A, if our first derivative is negative for any x value that's greater than A, then f has a local max. So just showing this graph, if we have an endpoint here, we could still describe that as a local max. Or like over here, we could say that's a local min. Same thing here and here. So just make sure you're familiar with the items in this theorem. All right, so we are going to take a look at concavity here. We'll understand and apply the meaning of the second derivative of a continuous function. So let's first just make a little sketch of a graph. Make it look like this. We'll just call this y is equal to f of x. And just kind of pointing out some special key points here. So we could say right about here, we would have a relative min. Up here, we would have a relative max. And I kind of led into this before. When a function changes concavity, so anywhere that we're looking at kind of like something opening up or a smile shape, we're going to say this is concave up. So right here, our function is concave up. Over here, this is described as being concave down. And right where it changes concavity, which looks like right about here, we call this a point of inflection or an inflection point. It's the point in which the concavity changes. So we're going to write this out for concavity. If our second derivative is positive, then f is concave up. If our second derivative is negative, then f is concave down. We could abbreviate. We could use CU for concave up. We could use CD for concave down. So again, concave up is just like this, a smile, a frown for concave down. And something else that's kind of interesting here, and I'll come back to this. Let's go ahead and say concave up would look like this. And we're going to apply this or relate it to the tangent lines. So wherever a function is concave up, all of our tangent lines are going to be below or under the function. If we're looking at concave down, all of our tangent lines are going to sit above the function. So that's just something to keep in mind. All right, so back to this little list or summary here. So again, if our second derivative is positive, that indicates our function is concave up. If our second derivative is negative, that indicates our function is concave down. And if our second derivative is 0 or it's undefined, that means we have a possible point of inflection at that x equals c. So I say possible, that's only if concavity changes. We'll just say the critical number. All right, so we're just going to look at one example, but we're going to analyze it quite a bit. So not only are we going to practice again intervals where our function is increasing, decreasing, and any extrema, but now we'll also take a look at a second derivative test. So these are all the directions on page 204 from 7 through 12, parts A through F, the analytic method. First, we're asked to find the intervals on which the function is increasing, decreasing, concave up, concave down, local extrema, inflection points. And then at the very end, we'll support our answers graphically. So let's go ahead and begin. We're going to go through this together. All right, so first we want to find our first derivative. This is just going to become negative 6x squared plus 6x plus 36. We're going to ask ourselves the two questions about this. Where is f prime of x equal to 0? Where is f prime of x undefined? Again, because f of x is a polynomial function, its derivative is as well, so it's never undefined. But we're going to set this equal to 0. Just like the ones we practiced yesterday, we're going to factor, solve by factoring. So we can factor out a negative 6. Watch your signs. So we'll get an x squared minus x plus 6. And as I say that, watch your signs. We're going to minus 6. So as we factor this, this will become an x minus 3 and an x plus 2. So our critical numbers are x equals 3 and x equals negative 2. Critical numbers for the first derivative. So now we're going to justify. So f prime of x in our number line here, we'll have a negative 2 and a 3. And again, I'm going to use the factor form. So f prime of x is equal to negative 6 times the quantity x minus 3 times the quantity x plus 2. So we could test a negative 3, we could test a 0, we could test a 4. So anything to the left of negative 2, we're starting with our negative 6, then we'll have another negative, and then another negative. So this will be negative over here. Let's say x is 0. We'll get a negative times a positive, so we're positive in between. And then anything to the right of 3, we'll get a negative times a positive times a negative, so we're back to negative. So we know that f of x is decreasing, then increasing, and then decreasing again. So we'll come back to that to answer the parts. Now let's go through our second derivative. So we're looking at this to take the derivative of once more. So we'll get a negative 12x plus 6, so that's nice. We're going to ask ourselves our same two questions about our second derivative. Where is f, our second derivative, equal to 0? And is our second derivative undefined? Again, undefined is never for this example. But here we'll set negative 12x plus 6 equal to 0. So 6 will equal 12x, and x is going to equal 2. So we have a critical number here. Why can't I divide right now? 1/2. Divide by 12. So our critical number is 1/2. So now we're going to make a number line for our second derivative. And we only have one critical number here, 1/2. So we're going to substitute it back into negative 12x plus 6. I could test a 0. I could test a 1. So when x is 0, we're going to get a positive value. And when x is 1, we're going to get a negative value. So this tells me my function is concave up before the 1/2, concave down after. And this tells me because concavity changed, there's a point of inflection at x equals 1/2. Up here, we could say there is a relative, if we're going from decreasing to increasing, we know there's a relative min at x equals -2. Increasing to decreasing, we know there's a relative max at x equals 3. So now we're going to put all the pieces together. So we could answer the first 4 parts, or the easiest. A is increasing, and that's between -2 to 3. B is decreasing, go back up to that number line, from -infinity to -2 and from 3 to infinity. C will say concave up from -infinity to 1/2. D concave down from 1/2 to positive infinity. All right, now for E and F, again, going back to this, we just want to find the local extrema. So this is just finishing the ordered pairs on of the function. So let's add a page here. All right, so our local extrema, we are going to calculate. We need f of -2 and f of 3. And for our point of inflection, we need f of 1/2. All right, so -2 cubed is -8 times a -2. That's going to give us a 16. -2 squared is 4, so that's going to give us a plus 12. Then minus a 72 minus a 1. This will give us 28 minus 73, which is a -45. F of 3 becomes 27 times -2, so a -54. Then we'll get a plus 27 plus a 108 minus a 1. And again, I want you to be able to do this, even if you have to write out some more in between steps, do this without a calculator. But we could look at this as 135 minus 55, so that's 80. So right now, we can answer part E. We have a relative min, which is the -45, when x is -2. We have a relative max, which is 80, when x is 3. All All right, let's calculate f of 1/2. We're still going to do this without a calculator. We're going to get -2. 1/2 cubed is 1/8 plus 3 times 1/4 here when we square 1/2, so we'll say plus 3/4. Half of 36 is 18 minus 1. So we get -1/4 plus 3/4 plus 17. So we get 2/4 or 1/2 plus 17, so we can say 17.5 or 35 halves. That wasn't too terrible. And then for part F, we would just say the point of inflection, again, is an ordered pair, 1/2, comma 17.5. So now we're finding out a lot more to help us pinpoint, quite literally, where our point of inflection is, and also to understand and know the concavity of our function. All right, so attached to this post today in Classroom is the Inspire Doc 4.3. You just go through one more example, so please make sure you copy that down and try it out on a separate sheet of paper. Please continue with that number 44 as needed. Now on pages 203 to 204, 1 through 9 odd, and number 13. And then from the AP practice problems, number 76 off of page 19. Now, when it says graphing calculator, okay, that means you can actually use the graphs page to help you out, but no CAS feature, like no solve feature, no derivative feature. Only use your graphing calculator to help you out with that. All right, guys, take care. Let me know if you have any questions.